everyone, welcome to our channel Knowledge of Friends. Subscribe to our channel and click the bell icon for the latest update. आज हम लोग जो क्लास करने वाले हैं वो केमिस्ट्री की क्लास करेंगे, जो कि क्लास केमिस्ट्री की 131 क्लास है। आपकी इससे पहले मैं 130th क्लासेस करवा चुकी हूँ ऑलरेडी। अगर आप फर्स्ट टाइम हमारा चैनल देख रहे हो या अभी तक आपने हमारे चैनल को सब्सक्राइब नहीं किया है, सो इट्स अ रिक्वेस्ट कि आप हमारे चैनल को सब्सक्राइब करो सो दैट हम जो भी वीडियोस डालें वो आपके पास सबसे पहले पहुँचे। एंड सेकेंडली, अगर आपको हमारा वीडियो अच्छा लगे तो प्लीज़ हमारे वीडियो को लाइक, शेयर और सब्सक्राइब करो। Now moving on with the concept that we have to start with, that is your bond parameters. Bond parameters क्या होते हैं that we have to discuss. With respect to the bond parameter, we have a bond length, then we have a bond angle. There are many bond parameters that we will discuss here in the class. So now it's a request, अगर आप हमारे चैनल फर्स्ट टाइम देख रहे हो तो प्लीज़ हमारे चैनल को लाइक, शेयर और सब्सक्राइब करो। स्टार्टिंग विद द बॉन्ड पैरामीटर, जो फर्स्ट है वो आपका बॉन्ड लेंथ है। लेट्स सी व्हाट इज बॉन्ड लेंथ। Bond length is defined as the equilibrium distance between the nuclei of the two bonded atoms in a molecule. एक मॉलिक्यूल में अगर दो बॉन्डेड एटम है तो उनके बीच में जो डिस्टेंस है, अगर वो इक्विलिब्रियम है तो उनके न्यूक्लियाई के बीच में जो डिस्टेंस है, दैट इज नोन एज बॉन्ड लेंथ. ओके, for the bond length only, the bond length are measured by the spectroscopic X-ray diffraction. जो bond length हम नापते हैं, क्योंकि ऑब्वियस सी बात है, आपको भी पता है कि जो न्यूक्लियस होते हैं हम उसको एक नेकेड आइट से नहीं देख सकते. ओके, तो इस वजह से हमें मॉलिक्यूल के न्यूक्लियस को हम नेकेड आइट से नहीं देख सकते. इस वजह से हमें उसके लिए स्पेक्ट्रोस्कोपिक एक्सरे डिफ्रैक्शन को देखना के थ्रू देखना पड़ता है. एंड द इलेक्ट्रॉन डिफ्रैक्शन टेक्निक्स, These over each atom of the bonded pair contributes the bond length. क्योंकि जितने भी आपके bonded pairs हैं वो सब के बीच में bond length होता है, तो वो हम हमेशा या तो स्पेक्ट्रोस्कोपिक एक्सरे से देखते हैं, स्पेक्ट्रोस्कोपिक वे से देखते हैं, एक्सरे डिफ्रैक्शन से देखते हैं, या फिर इलेक्ट्रॉन डिफ्रैक्शन टेक्निक्स. ये टेक्निक्स ऐसी हैं, ये मेथड ऐसे हैं जिसके थ्रू आप मॉलिक्यूल्स के बॉन्ड लेंथ को मेजर कर सकते हो, देख सकते हो, सिग्निफाई कर सकते हो. With respect to that, in the case of the covalent bond, अगर हम covalent bond का बात करते हैं, the contribution from each atom is called the covalent radius of that atom. अगर हम बात करते हैं in the case of covalent bonding, तो contribution जो होता है हर एक atom का, that is called your covalent radius of that atom. Now coming to the covalent, what is covalent radius? So now we had talking about the bond length only. With reference to the bond length, we have to understand what is covalent radius. Where the case of the covalent radius, you can say that the contribution of each an atom is called covalent radius of that particular atom. So the covalent radius is measured approximately as the radius of the atom's core, which is in contact with the core of adjacent atom in a bonded situation. If they are in the bonded situation, the core atoms, they are contact with each of the core of the adjacent atom, and the covalent radius is measured approximately as the radius of that particular atom's core, and that which they are in the contact and the core of the adjacent atom, that is bonded in the bonded situation. Okay, now coming to the next point for the covalent radius as well. The covalent radius is half of the distance between two similar atoms joined by a covalent bond in the molecule, in the same molecule. Okay, so for the covalent radius की अगर हम बात करते हैं, for the covalent radius that is the half of the distance, वो half होता है distance का between the two similar atoms that are joined by the covalent bond by the same molecule only. This is the covalent radius, where it is the half the distance between the two similar atoms that is joined by the covalent bond in the same atom. That I think you had understood. Now moving on with the next point that we have is in see here, the van der Waals radius represent the overall size of atom. जो van der Waals radius है वो आपका represent करता है overall size of atom का, which include its valence shell in non-bonded situation, जो कि उसका valence shell को include करता है with in a non-bonded situation. Now coming to the next point, that is further the van der Waals radius is half of the distance between the two similar atoms in the separate molecules in a solid. The van der Waals radius is half of that distance between the two similar atoms in the separate molecules in the solid. as well as if I'm talking about the typical averages bond length for a single, doubled and triple bond are. अगर हम typical average bond देखते हैं single bond के लिए, double bond के लिए, as well as for the triple bond, so you can see that here the bond type with their covalent bond length. So with respect to that you can understand the bond type with their covalent bond length, that is measured in pm. So here अगर OH single bonded जो है, OH जो ऑक्सीजन और हाइड्रोजन सिंगल बॉन्डेड है, तो वो आपका उसका कोवलेंट बॉन्ड लेंथ जो होता है वो 96 होता है. फिर कार्बन और हाइड्रोजन की अगर हम बात करते हैं, दिस इज ऑल्सो इन द सिंगल बॉन्डेड, दैट इज अ बॉन्ड टाइप, एंड द कोवलेंट बॉन्ड लेंथ इज 107 यू कैन से. नाइट्रोजन एंड ऑक्सीजन की बात करते हैं, दिस इज ऑल्सो अ सिंगल बॉन्डेड एंड द कोवलेंट बॉन्डिंग ऑफ दैट लेंथ इज 136. Next is your carbon and oxygen. Here the carbon and oxygen is also a single bonded and the covalent bond is 143. So the next is your carbon and nitrogen. This is also the single bonded, and this covalent bond length that we have is 143, as similar to the carbon oxygen. With respect to the carbon, if I'm talking about, this is the carbon single bonded, and the covalent bonding that it has is 154. कार्बन और ऑक्सीजन की बात करते हैं तो ये डबल बॉन्डेड होता है, डबल बॉन्डेड आपका होता है कॉम्बिनेशन. इसकी कोवलेंट लेंथ होती है 121. नाइट्रोजन और ऑक्सीजन की बात करते हैं, दिस इज ऑल्सो द डबल बॉन्डेड एंड द लेंथ ऑफ कोवलेंट बॉन्डिंग इज 122. Carbon and carbon, when it is combined with the double bonded, then it have a covalent bonding 133. Next is your carbon and nitrogen with double bonded, double electron sharing, then its covalent bonding is 138. Next is your carbon and nitrogen when they are sharing 3 electrons one to each other, and they are forming the triple bond where it has a covalent bond length that is 116. If I'm talking about the carbon and nitrogen when they are sharing the 3 electrons each, then the triple bonding sharing here and it forms a covalent bonding is 122. So this is the average bond length for the some single bond, triple bond, and of course your double bond. So these were the figures here. Now moving on with the next that we have is bond lengths for the sum common molecules. If I'm talking about the bond lengths of the sum of the common molecules, here they are the molecules given, and of course there is a bond length that is measured in the pm only. So the H2 molecules, that means H और H दोनों दो हाइड्रोजन आपके combine करेंगे with a single bond, and they have a bond length is 74. If I'm talking about F2, they are fluorine combination, then it forms 144 bond length they have. Chlorine and chlorine is combined, that is they form the Cl2, and it has a bond length of 199. Br2, that is bromine and bromine is combined to one another forming a single bond and having a bond length of 228. This is I2 and this is iodine, and iodine combine with each other and form I2 and having a covalent bond length that is 267. Nitrogen N2, that is nitrogen bond 3 electrons sharing with another nitrogen and forming a triple bond and having a covalent bond 109. Oxygen O2, that oxygen dioxide, this is oxygen and oxygen combined with the 2 sharing of electron having a double bond and forming a covalent bond length that is 121. Or then you will have your HF, that is your H is combined with fluorine, hydrogen is combined with fluorine and having a covalent bond of 92. Hydrogen is combined with Cl, that is chlorine, and HCl formation is taking place and covalent bonding is 127. Hydrogen is bonded with bromine and forming an HBr and having a covalent bond that is 141. Then hydrogen is combined with iodine and forming an Hi, that is and having a covalent bond 160 here. Bond lengths, these were the bond lengths of some common molecules. Now talking about the bond angles that we have to discuss here. With respect to the bond angles, it is defined as the angle between the orbitals containing bonding electron pair around the central atom in a molecule / complex ion. बेसिकली अगर हम बॉन्ड एंगल की बात करते हैं तो इट इज डिफाइंड एज द एंगल, ये डिफाइन किया जाता है एक एंगल जो बनता है ऑर्बिटल का, जो कि बॉन्डिंग इलेक्ट्रॉन पेयर्स कंटेन करते हैं, जो कि सेंट्रल एटम से बनता है मॉलिक्यूल्स में या कोई कॉम्प्लेक्स आयन से अगर तो उसमें बनता है, तो वो अभी मैं दिखाऊंगी भी कैसे फॉर्मेशन बनता है. ओके, विद रिस्पेक्ट टू द बॉन्ड एंगल, इफ आई एम टॉकिंग अबाउट बॉन्ड एंगल इज एक्सप्रेस इन डिग्री. बॉन्ड एंगल जो है वो हमेशा डिग्री में एक्सप्रेस किया जाता है, विच कैन बी एक्सपेरिमेंटली डिटरमाइंड बाय द स्पेक्ट्रोस्कोपिक स्पेक्ट्रोस्कोपिक मेथड, स्पेक्ट्रोस्कोपिक मेथड के थ्रू आप उसको एक्सप्रेस भी कर सकते हो और डिटरमाइन भी कर सकते हो एक्सपेरिमेंटली बाय यूजिंग द स्पेक्ट्रोस्कोपिक मेथड. You can find the bond angle also, that is expressed in the degree as well. Now moving on with the next point for with respect to the bond angle that we have is with respect to it gives some idea regarding to the distribution of orbitals around the central atom in a molecule or a complex ion, and hence it help us in the determining its shapes. For example, H2O की बात करते हैं, 2 hydrogen is combined with 1 oxygen, an angle in water that can be represented as, you can say that this is the bond angle that is shown in the H2O molecule, where 2 hydrogen are there and 1 oxygen is there, and having a 3 lone pair with having a 6 electron, they are not sharing with each other. One electron is sharing with hydrogen, and to make the stability, and the bond angle they formed is 104.5 degrees Celsius. So they are making 104.5 degrees Celsius angle between 2 hydrogen between the center atom, that I had told you before also. Now coming to the talking about the bond enthalpy. What is bond enthalpy here? So bond enthalpy, it is defined as the amount of energy required to break 1 mole of bonds of a particular type between the 2 atoms in a gaseous state. एक gaseous state में ये basically हम जितनी energy हमें required होती है एक 1 mole of bond को break करने के लिए एक particular type में 2 एटम के बीच में, तो वो हमारी बॉन्ड इंथैल्पी होती है. विद रिस्पेक्ट टू द यूनिट ऑफ द बॉन्ड इंथैल्पी इन केजी मोल इनवर्स, अगर हम बात करते हैं यूनिट जो बॉन्ड इंथैल्पी की यूनिट होती है, दैट इज किलो जूल मोल इनवर्स. फॉर एग्जांपल फॉर द हाइड्रोजन बॉन्ड, जो कि हाइड्रोजन सिंगल बॉन्डेड होता है, बॉन्ड इंथैल्पी इन हाइड्रोजन मॉलिक्यूल इज 435.8 किलो जूल मोल इनवर्स. तो अगर हाइड्रोजन जब कॉम्बिनेशन करते हैं तो दे फॉर्म अ बॉन्ड hydrogen molecule that the bond enthalpy that they are used for, that is 435.8 kilojoule mole inverse here. Now seeking of that only, that we have to start with the hydrogen bonding, that is H2, that are in the gaseous state, and that break it out with having a bond enthalpy, having a hydrogen in the gaseous form and another hydrogen in the gaseous form, and the bond enthalpy that they had formed is 435.8 kilojoule mole inverse, that I had said you before also. Similarly, the bond enthalpy for the molecules containing the multiple bonds, for example O2 and N2, that is oxygen dioxide and dinitrogen oxide. So of dinitrogen will be in the form of O2. O2 की बात करते हैं तो they formed a double bond here, okay, and when they break this, so oxygen in the gaseous state, whereas the oxygen is the gaseous state only, and the bond enthalpy that they had formed is 498 kilojoule mole inverse. This is in the case of the oxygen dioxide, okay. डाइऑक्साइड के केस में है ये, जिसमें आपकी जो बॉन्ड एंथैल्पी होती है वो 498 किलोजूल मोल इनवर्स होती है. नाउ विद रिस्पेक्ट टू द हाइड्रोजन डाइऑक्साइड जो H2 होता है, उसके लिए हमारा जो बॉन्ड एंथैल्पी होती है that is 435.8 kilojoule inverse, and with respect to the oxygen that is 498 kilojoule mole inverse. Now moving on with the next, that we have for the Now moving on with the nitrogen atom, that N2, that is N is sharing with the triple bond with nitrogen, that is are in the gaseous state, and when it is break down, then N plus N that is the case of gaseous state, and the having a bond enthalpy that is 946.0 kg mole inverse. So the bond enthalpy for the N2 is 946.0 kg, that is kilojoule mole inverse. It is important that to the larger bond dissociation enthalpy, stronger will be the bond in the molecule for a heteronuclear diatomic molecule like HCl that we have. Here you can see that it forms H plus and Cl minus. That is important that the larger bond dissociation enthalpy, stronger will be the bond in the molecule, and for heteronucleus diatomic molecules like HCl we have. Here you can see the reaction for the HCl only. So HCl जो होता है that is in the form of the gaseous state. When it is break down, then it is formed as H, that is in the form of H plus ions, and as phos, that is in the Cl minus. that are in the gaseous state only. The bond enthalpy that they form for the in the case of the HCl here, that is 431.0 kilojoule mole inverse here. In the case of the polyatomic molecules, the measurement of the bond strength is more complicated. For example, in the case of H2O molecules, the enthalpy needed to break the 2O oxygen with combination of the hydrogen bond is not at the same. Now talking about the hydrogen here, that is a molecule of your water, that is H2O here. When it is break down, then it forms H plus and OH minus, that it forms in the gaseous state only, and the bond enthalpy that they form is 502 kilojoule mole inverse. Now talking about the OH minus that it forms is H plus and O minus. With respect to the bond enthalpy with OH molecule is that they formed, and the enthalpy that they are using it 427 kilojoule mole inverse. The difference in the enthalpies values shows that the second OH minus bond undergoes the some change because of the change chemical environment. That is the reason for the some difference in the energy of the same OH minus bond with the different molecules like C2H5OH, which is ethanol, and water. Ethanol and water के लिए जो हमने बताया था अभी वो with respect to that. Therefore, in that case, if I'm talking about for the polyatomic molecules, the term mean and average bond enthalpy is used. For the polyatomic molecule, if I'm talking about the term of that mean and average bond enthalpy that is used, it is obtained by dividing the total bond dissociation enthalpy by the number of bonds broken by expressed below in the case of the water molecules. Where the bond enthalpy की बात करते हैं, then we have an average. Of course, mean में निकालना पड़ेगा the sum of all upon the number of the quantities, that is upon 2, and then we get 464.5 kilojoule mole inverse. That according to that we can find the bond enthalpy, the average bond enthalpy of any of the molecule that we have. Now talking about the bond order here, bond order with respect to in the Lewis descriptions of covalent bond, the bond order is given by the number of bonds between the two atoms in a molecule. If I'm talking about the Lewis description of covalent bond, then the bond order is given in the number of the bond that is between the two atoms in the molecule. The bond order, for example, is H2 with a single shared electron pair, and O2 with the shared electron pair, and the N2 with the shared with the 3 shared electron pair. Okay, and as 1 2 3 respectively. So with respect to the H2 and with O2 and N2, it have a 1 as well as it have a 2 and it have a 3, with respectively they have a bond order. Then similarly in the carbon monoxide, there are 3 shared electron pairs between the carbon and oxygen, and the bond order is 3. For N2, bond order is 3, and it is your bond enthalpy is 946 kilojoule mole inverse, being one of the highest for a diatomic molecule. This is the highest for the diatomic molecule, that the bond enthalpy that we have. Now moving on with the next that we have is further in isoelectronic molecules, and the ions have an identical bond orders. For example, F2 and O2 minus 2 minus have bond order 1, N2 and CO and NO plus have a bond order of 3. A general correlation useful for the understanding the stabilities of the molecule is that with increase of the bond order, bond enthalpy increases and bond length is decreases. जैसे जैसे आपका जो bond order है अगर वो increase होता जा रहा है तो bond enthalpy भी increase होगी, but bond length जो होगा वो आपका decrease होगा with reference to understanding the stabilities of that molecules. Now talking about the resonance structure here, what are the resonance structure? That it is often observed that a single Lewis structure is inadequate for a representation of molecule is conformity with the experimentally determined parameters. For example, the ozone, that is O3 molecules, that can be equally represented by the structure 1 and 2. Here you can see the structure of ozone, that is O3. Here they are forming one single bond, that is of 148 pm, and of course that is double bonded, that is 121 pm for the oxygen bonding here. With respect to this is the first structure here, and this for the second structure, this double bond on the left side, and in the first structure the double bond is on the right side. In the double bond on the left side having a your bond length is 121 pm, and with the single bond 148 pm respectively. Now, with reference to the oxygen, that is OT, the third form that we have, oxygen is one with a single bond and with the dotted pair, that is 128 pm and 128 pm, with respectively the same in other cases. And here it is the resonance of the O3 molecule. With reference to the resonance, the structure 1 and structure 2 represent the two of the canonical forms, while the structure 3 of the resonance form are a hybrid form. Okay, so this is the hybrid one, you can see, and this is the canonical form, and this is also the canonical form, and this is your hybrid form of ozone O3 molecule respectively. Now, moving on with the next that we have is, in both structures we have a oxygen single bond, oxygen single bond, and oxygen double bonds oxygen. The normal this is single and the double bond length was 48 pm and 121 per respectively. So basically 148 for the single bond and 121 for the double bond only. Experimentally determined oxygen's the bond length of the O3 molecule are the same, 128. Thus the oxygen and oxygen bond of O3 molecules are intermediate between a double and a single bond. These were the dotted line that we had represented in the third structure. This is the intermediate between the single bond and the double bond. Okay, this is the intermediate condition that we have 128 pm. Now moving on, according to the concepts of the resonance, अगर resonance के हम concepts की बात करते हैं, so wherever the single Lewis structure cannot be described a molecule accurately, a number of structure with the similar energy positions of nuclei, bonding and non-bonding pairs of electron are taken as a canonical structure of the hybrid, which describes the molecule accurately. Where in the case of the ozone, that O3 molecule, I had explained you about the canonical form that it forms with a single and double bonded pair of the O3 molecules, and as well as the canonical form, there the two figure that had shown the double bond in the left side and in the another figure that we had mentioned here with respect to the double bond on the right side. But for the O3 molecule in the hybrid condition, they are the partially the intermediate condition between the single bond and the double bond here. So some of the other examples of the resonance structures that are provided by the carbonate ions and carbon dioxide molecules. So जो intermediate resonance structure की हम बात करते हैं तो कुछ examples जिसमें से आपका एक carbonate ion और carbon dioxide molecule भी है. The question that we have with respect to the carbonate only, so they explain the structure of CO3 2 minus ion in terms of the resonance. So in terms of resonance we have to explain this. Okay, the single Lewis structure based on the presence of the two single bond and the one double bond between the carbon and oxygen atom is inadequate to represent the molecule accurately, as it represents the unequal bond. Then moving with the structure that we have is, according to the experimental findings, all the carbon to the oxygen bonds in the carbonate ion, that is CO3 2 minus, are equivalent. Therefore, the carbonate ion is the best described as a resonance hybrid of the canonical form, that is first, second and the third, that is shown below. Here you can see the carbonate ion where the double bonded with oxygen and having a 2 lone pair. With respect to here, it is a 3 lone pair and the 3 lone pair with respectively. In the case, so this is the first figure where it is showing the resonance in the carbonate ion with the 1, 2 and the 3 figures that represent these the canonical form only. So these were the canonical form. Here it is the second one where it is double bonded with this atom and having a 2 lone pair, with respectively the other two are having a 3 lone pair, and the same for the other. Then they have a this is rotation, this is the upward, this is the leftward, and the second one, third one is on the right side. They're the same and having a canonical form only. So this is on the form of the canonical form only, and this is also in the form of the canonical form. Explain the structure of the carbon dioxide molecule. आपको structure समझाना है, और with respect to the carbon dioxide molecule, the experimentally determine the carbon to the oxygen bond length in the carbon dioxide is 115 pm. The length of the normal carbon to oxygen double bond and the carbon to oxygen triple bond are 121 pm and 110 pm respectively. 121 for with respect to the double bond, and of course for the 110 for the triple bond. The carbon dioxide bond on the CO2 is 115 pm, lie between the values for the carbon double bonded oxygen and carbon triple bonded oxygen. Obviously, a single Lewis structure cannot be depicted in the position at it becomes necessary to write more than one Lewis structure, and to be considered that the structure of the carbon dioxide is best described as a hybrid, as well as the canonical as resource form, first, second, and the third. Now moving on with the next that we have is, here you can see that the sharing of two electron with respect to the other molecule. This is the combination where they are mixing with each other, and they are forming the structure that is CO2. Okay, then after that, with respect to this only, this is the O. Okay, C1C, and then there is O, then the two lone pairs with respect to the oxygen only. This is the second, and this is the third with respect to same only. They are the foundation of covalent bonding with resonance in the carbon dioxide molecule with 1 2 3, and they are in the canonical form. This is also in the canonical form. This is also in the form of canonical form, and this is also canonical form. In general, it may be stated that resonance stabilizes the molecule as the energy of the resonance hybrid is less than that the energy of any single canonical structure. Resonance averages the bond characteristics as a whole, thus the energy of O3 resonance hybrid is lower than either of the two canonical forms, that 1 and 2 that we had mentioned here in the above. Many misconceptions are associated with the resonance at the same need to be dispelled. The canonical form have no real existence. Basically, the canonical form का कोई real existence नहीं होता. The molecule does not exist for a certain fraction of time in a canonical form and for other fraction of time in the another canonical form. So if I'm talking about the molecule that they have existence here, so it forms in this for some fractions of time for this particular canonical form, and the next for the some fraction of time for the next other canonical form that they are formed. There is no such equilibrium, ऐसा कोई such equilibrium नहीं होता between the canonical form as we have between the atomic jet we have for the tautomeric form, that we can say the cato and enol in the tautomerism. Okay, so now moving on with the next with the respect to the tautomerism also, tautomerism and the which having a combination of the keto and enol here. So the molecule as such has having a single structure which is resonance hybrid of the canonical form, and which cannot as be depicted by the single Lewis structure as well. Now talking about the polarity of bonds, what are the polarities of bond, how do polarity of bond signifies? So polarity of bond, the existence of the 100% ionic or the covalent bond represent an ideal situation. In reality, no bond and the compound is either completely covalent or ionic. Even in the case of the covalent bond between the two hydrogen atom, there is some ionic character as well. When covalent bond is formed between the two similar atoms, for example that is H2, that is hydrogen dioxide and dihydrogen dioxygen, and chlorine Cl2, then N2 and F2, the shared pair of electron is equally attracted by the two atoms. As a result, electron pair is situated exactly between the two identical nuclei. The bond so formed is called non-polar covalent bond. Okay, जो bond बनता है, जो हमारे similar electron similar जो atoms होते हैं, they form a pair of electron in the equally attracted to one on each other, and as well as they form an electron pair that is situated exactly between the two identical nuclei, and that these bonds were so formed, and they are formed and they had known as non-polar covalent bond as well. Now contrary to this, in the case of the heteronuclear molecule like HF and the shared electron pair between the two atoms that get displaced more towards the fluorine, since the electronegativity of the fluorine is far greater than that of the hydrogen, and the resultant covalent bond is your polar covalent bond. With respect to the polar covalent bond, if I'm talking about the H and F, so fluorine having a high electronegativity, and it is a far greater than that of the hydrogen, so the resultant covalent bond is a polar covalent bond only. Now moving on, as the result of the polarization, the molecule passes the dipole moment. जो polarization की बात करते हैं, if the molecules they are forming a dipole moment, which can be defined as the product of the magnitude of the charge and the distance between the centers of the positive and the negative charge. It is usually distinguished by a Greek, that is the signification of this. It is okay. With respect to the dipole moment is represented by the sign and the charge multiplied distance of the separation. The distance of the separation represented by the r, and the charge is represented by the q. So the formula that we form is the dipole moment equals to charge multiplied distance of the separation here. Dipole moment is usually expressed in the diab units, and the conversion factor 1 diab equals to 3.33564 into 10 to the power minus 30 cm, where c is the coulomb and m is the meter. So coulomb meter, 1 diab equals to 3.33564 into 10 to the power minus 30 coulomb meter. For the dipole moment in a vector quantity, if I'm talking about the dipole moment, dipole is a vector quantity and is depicted by the small arrow with the tail of positive centers and the hand pointing towards the negative center. Head is pointing to the negative center, and the tail is representing the your positive center. For example, the dipole moment of HF, and that is your H here and then F here, one of the electron sharing that they are forming the stability, and this is the positive end, so the tail is here and the head is on the side of the negative charge. The shift of an electron density is symbolized by the covered arrow that is here and above the Lewis structure to indicate the direction of the shift as well. In the case of the polyatomic molecules, the dipole moment not only depend upon the individual dipole moments of bond that are known as bond dipoles, but also be the spatial arrangement of various bonds in the molecule. In such case, the dipole moment of a molecule is a vector sum of the dipole moments of various bonds. For example, the H2O molecules, which has best bent in structure, the two OH minus bonds are oriented at an angle of 104.5. Net dipole moment of 6.17 into 10 to the power minus 30 coulomb meter. 1 dibe equals to 3.33564 into 10 to the power minus 30 coulomb meter, where is the resultant of the dipole moment of the oxygen and hydrogen bond that they are forming here. You can see with the structure here, oxygen, which H2O, here the H2 and H plus is the signification of plus, so here it is the tail and there it is the head with the oxygen, and of course here it is a head tail, and here it is a head with an oxygen within side of an oxygen, because it is negative electron and that is a bond dipole. With a triple bond, here you can see that oxygen hydrogen, the combination of hydrogen oxygen, and the resultant dipole moment, because they are coming towards the hydrogen oxygen only, and that gives the dipole moment, resultant dipole moment after the oxygen. The dipole moment in the case of the BF2, अगर हम BF2 की बात करते हैं तो dipole moment क्या आता है, that is of course 0. This is because the two equal bond dipole point is opposite direction and cancel the effect of each other. In the case of the dipole moment in the case of BF2, where it is 0, because this is because the two equal bonds dipole moment is opposite direction, and that cancel out the effect of the each other, and that here you can see that BE and this is F and this is F. BeF2, where bond dipole in the BeF2, this is F is highly negatively element with respect to the Be. So it goes to the head, goes to the fluorine, head goes to the fluorine, where the total dipole moment is BF2. In the tetraatomic molecules, for the example BF3, the dipole moment is 0, although the BF bonds were oriented at an angle of 120 to one another, and the 3 bond moment give a net sum of the zeros. As the result of any two equal is equal and opposite to the third angle, and BF3 with the bond dipole, and of course the fluorine having a negative electron here. सो हेयर इन द केस दैट BF3, तो फ्लोरीन जो है वो आपका निगेटिवली ज़्यादा इलेक्ट्रॉन है एटम है, तो इस वजह से जो हेड है आपका वो फ्लोरीन की तरफ है. ओके, so this is the bond dipole, and of course there is they have a two-sided with having a different direction, so total dipole moment will be the 0 only here in the cases. Now moving on with the next that we have is, just as all the covalent bond have some partial ionic character, The ionic bond also have a partial covalent character. The partial covalent character of the ionic bond was discussed by the Fazans in the term of the following rules. The smaller the size of the cation and the larger the size of the anion, the greater the covalent character of an ionic bond. जितना ज़्यादा आपका साइज होगा कैटायन का उतना ज़्यादा आपका एनायन का साइज होगा, और जितना ग्रेटर आपका कोवलेंट कैरेक्टर होगा उतना ही आपका आयनिक कैरेक्टर भी होगा. The greater the charge on the cation, the greater the covalent character of the ionic bond we can see. जितना ज़्यादा आपका cation पे चार्ज होगा उतना ज़्यादा आपका covalent character होगा और आपका ionic bond में. For the cation and the same size and the charge, the one with the electronic configuration that is n-1 d0 ns0 with typically of the transition metal is more polarizing than one with a noble gas configuration that is ns2 np6 typically of alkali and alkaline earth metal cations. Now the cation polarizes the anion, pulling of the electronic charge towards itself and thereby an increasing of electronic charge between the two as well. The polarizing power of the cation, the polarizability of the anion and the extent of the distortion that is polarization of an atom are the factors. These were the factors that are dealing with. Okay, so class आज के लिए इतना ही. Thank you. Hope you enjoy this video. If you like this video, please give a thumbs up and give a suggestion in comment box. Please like, share and subscribe our channel so that many and maximum people can get the information at once. And if I'm talking about the cations, that जितना ज़्यादा आपका कैटायन पोलराइज होगा एनायन उतना ही आपका जो इलेक्ट्रॉनिक चार्ज होगा वो आपके करीब होगा, इटसेल्फ होगा, एंड इवन इंक्रीजिंग देयर इलेक्ट्रॉनिक चार्ज between the two also, and that the polarizing power of that particular cation, that polarizability of that particular ion also extend by the distortion polarization of an atom and other factors that they are moving with. And even though if I'm talking about the dipole moment, that I had told you about the charge that was multiplied by the distance of the separation that is represented by the r, and the charge that is represented by the q as well, and the dipole moment is mu, or represented by the mu only. With the result of the polarization, the molecular powers possesses the dipole moment, which can be defined by the product of the magnitude of the charge and the distance between the center of the positive and the negative charge. It is usually depicted by the mu only, and it shifts the shifts of the electron density is symbolized by the crowd arrow. That with a further arrow we can see that the tail of the positive center, positive side, and the head pointing towards the negative side, for example in the dipole moment here. Okay, in the case of polyatomic molecules, the dipole moment not only depends upon the individual dipole moment of the bonds and that are known as bond dipole, but also on the spatial arrangement of the various atoms as well. So class, hope you enjoy this video. If you like this video, please give a thumbs up and give a suggestion on a comment box. Thank you.